Now that we know enough about conditional expectations, we're going to start talking about stochastic processes. So this course is all about stochastic processes, that is to say, family of random variables, and we're trying to do calculus and analysis with such processes. So from an applied point of view, these families of random variables will be indexed by a parameter that represents time, and time can be modeled in a discrete way or in a continuous way. And we're going to start with the discrete because it's simpler to describe if you want from an applied point of view. From a more analytical point of view, the idea is that, well, the discrete time stochastic process will be the stochastic analog of the sequences that we've used in building integral and differential calculus back in first year, and the functions will be replaced by continuous time stochastic processes. Now we're going to start understanding sequences first, and as we do so, we'll see that the course is not about general stochastic processes, general sequences, general functions. It's about stochastic processes that have specific properties described in terms of conditional expectations. In particular, we'll be paying very special attention to martingales, and we'll see that martingales, from an applied point of view, are stochastic processes that model something that changes over time as information increases. And in doing so, it's such that at a point, let's say right now in the present, it is one of the possible evolution of what we had in the past, given the increase of information that happened between the past and the present. So if you take a conditional expectation of your family of random variables right now, given a point in the past, where you get back what your random variable was in the past. That's in non-technical terms, what a martingale is. So by being a martingale or variations thereof, our sequences or families of random variables will have very nice analytic properties. So this probabilistic property in terms of conditional expectation of being a martingale will imply analytic properties such as convergence in L2. That will be the main result of our chapter. So by restricting our attention to stochastic processes with specific probabilistic properties that are relevant in the applications we have in mind, in particular to finance, we'll get a whole range of nice analytic properties that are going to be critical in building the Ito integral, for instance, and our calculus of stochastic process more generally. So let me start with the key definitions in this chapter. The first definition is the definition of a filtration. So what is a filtration? It is a sequence of sigma algebras that is nested. So F0 is included in F1, which is included in F2, and so on and so forth. So you have a whole families of sub-sigma algebra, and it increases as time passes. So that's the natural number that index it increases. Right, so this is how we're going to model our increase of information over time. Now, whenever I have a probability space and a filtration of that probability space, I'm going to call any sequence of random variables a discrete time stochastic process, but I'm going to say that this process is adapted to the filtration if for every n, xn is fn measurable. So that's very important. We're going to only pay attention to processes that are adapted to a given filtration, right? So as time passes, we have different sigma algebras to represent the different level of information, and we always measurable with respect to the level of information at the time we are considering. So xn is fn measurable. Now obviously it's going to be fn plus 1, fn plus 2 measurable, but it may not be fn minus 1 measurable. It may not be measurable if you had fewer bits of information. Okay, now what is a martingale? So you give yourself a probability space and a filtration, and a martingale is a special kind of adapted stochastic processes. So we talk about L2 martingales or L1 martingales. In this course, we'll be mostly considering L2 martingales. So we quantitatively assume that Mn is not just Fn measurable, but also square integrable. And then we call it a martingale. You cannot be just a martingale with respect to nothing. Your martingale with respect to a given filtration. And if you change the filtration, certain things will stop being a martingale or start being a martingale. Your martingale with respect to a certain filtration, if you adapt it and you satisfy this property. So when you take the conditional expectation of Mn plus 1 given Fn, right? So you have a variable that is now Fn plus 1 measurable, and you force it to become Fn measurable. You take the projection down to the subspace of Fn measurable L2 functions, L2 process, then you get back Mn. Right. So it models this idea that Mn plus 1 is one of the possible evolution of Mn given our information has increased from Fn to Fn plus 1. Right, so that's the definition of being a martingale, and stochastic process satisfying this property will be the key focus of our entire course. Now, often, we need to relax this notion a little bit for certain applications, and we will look at submartingale. And what is a submartingale? Well, it satisfies not this equality here, but an inequality. That is to say, Mn is less or equal than the conditional expectation of Mn plus 1 given Fn. The reason why we need this notion of submartingale is because we'll see in a minute, actually that's a good exercise you can do right now based on properties of conditional expectation. If I start with a martingale and I take, let's say, its absolute value or its square, then what I get is a submartingale, but not necessarily a martingale. So there's all sort of modifications of martingales we're going to need to make, and this is going to turn our martingales into just submartingales. But what we're going to see is that a lot of the nice properties that we have for martingales actually hold also for submartingales. Okay, now notice that martingales very often occur as a function of a family of random variable. You have a sequence of independent random variable, and you take a certain function of this random variable, and this is very often how martingale occur under some conditions on this function. So what we're going to do now is have a look at a set of quintessential examples of discrete time martingales. Okay, so let me start with my favorite example for a martingale, or maybe one of my two favorite, the other one being the dyadic martingale that we'll see later in this chapter. This first example is the sum of independent IID random variables with mean 0. So I have xj, a sequence of random variables which are independent and identically distributed, and it doesn't really matter how they're distributed, but it matters that they all have mean 0. And I'm going to assume further that they are all in L2. That's to ensure that I have an L2 martingale. I could also assume that they're all in L1 and I'll get an L1 martingale. Okay, now I'm going to define Sn to be the sum of the xj when j runs between 1 and n. And I'm going to define my filtration Fn as being the sigma algebra, so Fn, the nth element of my filtration, is the sigma algebra generated by the first n of those IID random variables. Okay, and for the sake of initializing this whole thing, I'm going to put S naught to be 0, and I'm going to define F naught to be the trivial sigma algebra. And what I'm claiming is that Sn will then be a L2 martingale with respect to this filtration that I've just defined. Now, proving that involves three things. First of all, we need Sn for every n to be Fn measurable. That's going to make the process adapted. That's part of the definition of being a martingale. For every n, I'm going to ask Sn to be in L2. That's going to make it an L2 martingale. The reason why we have such a quantitative assumption, could be L1 rather than L2, but there has to be something, is to guarantee that the conditional expectation makes sense. And then we prove the key property, which is expressed in terms of conditional expectation, and says that the expectation of Sn plus 1 given Fn has to be Sn for all n. So let's go and do that. So first of all, take an n. Sn is the sum of the xj's. Now a finite sum of measurable random variable will be measurable itself. So all I need to show is that for every j between 1 and n, xj is Fn measurable. But Fn is the sigma algebra generated by all the xk up to n. So xj is in L2 of omega Fn for all j equal to 1n, since the sigma algebra generated by xj is included in the sigma algebra generated obviously by all the xk up to xn for all j between 1 and n. So Sn is therefore adapted. To the filtration Fn. Okay, that's good. We also have that because xj is in L2, a finite sum of L2, object is still in L2. So, moreover, Sn is in L2 of omega Fn p for all n. Okay, that's good. Now we get to the key property, the conditional expectation aspect. So what is the expectation of Sn plus 1 given Fn for a fixed n? Well, this is the expectation of xn plus 1 plus Sn by definition of Fn of Sn plus 1. Now you use the linearity of conditional expectation and you get that this is the expectation of xn plus 1 given Fn plus the expectation of Sn given Fn. But now, okay, now what have we got? Xn plus 1 is independent of Fn. Why is that? Because Fn is the sigma algebra generated by all the random variables up to n. In particular, it doesn't include xn plus 1. Now, xn plus 1 is independent of all the xj's before it. Actually, all of the other xj's. It's independent of x1 till xn. So it's independent of the sigma algebra generated by that, by definition. And we've seen in a little exercise in the last chapter that when you take the expectation of a variable that is independent of what you're conditioning upon, then what you get is just the standard expectation of this variable. Okay, and we've got that second part. Now looking at the second part, what have I got? I've got that the expectation of Sn given Fn is Sn, because Sn is Fn measurable. So given the take out what is known property of conditional expectation, this is equal to Sn plus the expectation of xn plus 1. Sn times, I'm skipping a step here, I should have said Sn times the expectation of the function constantly equal to 1. So let's say the indicator function of the full set given Fn. But now, this conditional expectation of the constant of a constant is just a constant. You can check that from the definition of conditional expectation. That's a very good exercise. So here you get Sn. And what is the expectation of xn plus 1? Well, that was part of our assumption that our IID variables had mean 0. So this is plus 0. And therefore, we've proven the Martingale property. Now, from an applied point of view, you should think of this example, sometimes called gambler's rune, as you're playing a fair game. So the game is fair because the expectation is 0. Different rounds of the games are independent of each other, and Sn is the sum. You imagine xj is your gain, and so Sn is the accumulated gain or loss over the course of the game. And what being a martingale tells you, what does that tell you? That the conditional expectation of Sn plus 1 given Fn is Sn. It tells you that the conditional expectation of Sn plus 1 minus Sn given Fn by the linearity of conditional expectation and the take out what is known property that we've used here has to be 0. So that is to say, given the information that you have at time n, what you expect to gain is 0. Right, and that really makes sense because you're playing a fair game. Okay, that's it for this first example. So in our first example, we looked at sums of IID random variables with mean 0. In our second example, we're going to do the next obvious algebraic thing to do with IID variables. We're going to take their products. This time we're going to assume that their expectation is 1. So we have xj, IID, random variables. We assume they're all in L2 for all j. And then we assume that the expectation of xj is 1 for all j. And we define the product up to n as the product of the xj, j equal 1 to n. We initialize that with p naught being 1, constant equal to 1. And again, we take Fn to be the sigma algebra generated by the first n random variable. That's going to be very often the way we define our filtration given a family of IID variables, and then we build our martingale as a function of these IID variables. And again, initialize with f naught being the trivial sigma algebra. Now, I want to show that Pn is an L2 martingale with respect to this filtration. Right, so again, 3 things to prove. The first 2 things are exactly as in the case of a sum. xj is in L2 of omega fn p for every j equal 1 to n. Let's fix an n. Right, that's because by definition fn is a sigma algebra that's generated by n random variable including xj. So that makes xj measurable with respect to fn, and it's in L2 because because that was part of my definitions. And now if I take a product of objects that are measurable and in L2, then I stay in L2 as a finite product. Okay, so that gives me the adaptedness of the process, and that gives me the quantitative information that it stays in L2. Now, the key thing to prove is the conditional expectation property. So I take the expectation of Pn plus 1 given Fn. What do I get? Well, this time it's a product, so this is the conditional expectation of Xn plus 1 times Pn given Fn. And I can take out what is known, take out what is known. And Pn is known, right? Pn is Fn measurable, so you can take it out of the conditional expectation. But now again, Xn plus 1 is independent of Fn, because Fn is the sigma algebra generated by x1 till xn, and x1 till xn are all independent of xn plus 1. So the conditional expectation, when I'm conditioning something by a sigma algebra and that something is independent of that sigma algebra, then all I get is the standard expectation, and I have asked all of my random variable to have expectation 1, so the expectation of xn plus 1 is 1. And that gives me exactly what I want. and prove that Pn is a martingale. Now for our last example, we'll do an intriguing modification of the first example. We'll start again with IID variables in L2 for j, and once again we're assuming that they have mean 0 and we form Sn to be the sum of the xj. But I'm going to be interested in what happened when I considered Sn squared, right? The square of the sum of these IID variable. And interestingly enough, this is not going to be a martingale, generally speaking. It would be a sub-martingale, but it wouldn't be a martingale. I'm going to have to compensate this square for it to be a martingale, and I'm going to have to compensate it in a way that's adapted to the variance of my random variables, my IID random variables xj. So I'm going to assume that the expectation of xj squared is, well, some fixed number that I'm going to call sigma square for some sigma positive. Okay, so now I'm going to define Mn to be, this time, Sn squared minus n times sigma squared. And the claim will be that Mn is an L2 martingale. Is an L2 martingale. Okay, with respect to what? With respect to Fn. Fn being the usual one, the filtration obtained by taking Fn as the sigma algebra generated by the first n IID variables, initializing with the trivial sigma algebra, and here we're going to initialize m0 as being 0. Okay, so same thing as before. Do we have an adapted process, and do we have the process in L2? And yes, that's true. Mn is in L2 of omega Fn P, since sum and products of measurable functions are measurable. Right, so our xj's are all in L2, and also should not have said of measurable functions, I should have said of L2 functions in L2. Let's say finite sums. So I'm just taking finite sums, finite product to form this square and add these numbers, importantly, and the constant function is in L2 also. Therefore, n times sigma squared, which is a constant random variable, is also in L2. Okay, now the real point is to prove the conditional expectation property. And here we'll see in proving that having made this modification of the square of the sum based on the variance was critical. And that would be a theme in this entire course, that there's extra terms that you would not necessarily expect in all sorts of formulas that we will see, like analogues of the fundamental theorem of calculus, that come from the fact that we are not dealing with just functions or with deterministic stochastic processes, but genuine stochastic processes, and they have a non-trivial variance. Right? If the variance were 0, if I was in the deterministic case, then this term here will disappear. And these correction terms based on variance are going to pop up everywhere in this course. Now, let's see in this simple example why we need it. Okay, so what is this? This is the expectation of Sn plus 1 squared minus n plus 1 times sigma squared given Fn. So let's expand that a little bit. So this is the expectation of Sn plus xn plus 1 squared minus, I'm going to keep that n squared fn, or do I? No, maybe I'm just going to keep that, and then subtract n plus 1 times sigma squared. That's because the conditional expectation of the indicator function of omega is just 1. So expanding this, I get the expectation of Sn squared given Fn plus 2 times the expectation of Sn times xn plus 1 given Fn plus the expectation of xn squared given Fn, xn plus 1, sorry, minus n plus 1 times sigma squared. Now what have I got here? Sn squared is Fn measurable, so you can take out what is known, and this first term is going to be just Sn squared, again because the conditional expectation of the indicator function of omega is just 1. In the second term, I'm going to take out what is known, and I get 2Sn times the conditional expectation of xn plus 1 given Fn. And then in the third term, I'm going to use independence. So here I've used take out what is known, and I've used independence. And the independence tells me, because xn plus 1 squared is independent of Fn, that this conditional expectation is just a plain expectation of xn plus 1 squared minus this correction term. Okay, so I get Sn squared. That's good. Let's put that here, minus n sigma squared, that's what I want. And then I get a minus sigma squared. Now this term here, again, I can use independence. That gives me plus 2Sn times the actual expectation of xn plus 1. What is the expectation of xn plus 1 squared? It's sigma squared. That's part of our properties of our IID variables. They have mean 0 and they have variance sigma squared. So the sigma squared here will cancel, and we need this minus sigma squared to cancel this term here. And now we get this here is mn, and the expectation of xn plus 1 is 0. So we've proven that mn is a martingale, and we really needed to have this correction term in order to do that. Right, this concludes this last example, and we will revisit especially example 1 and example 3 throughout the course. So it's very important to spend some time understanding why this reasoning of proving, for example 1 and example 3, the Martingale property works.